Uh, hey guys, how are you all doing? Uh, I hope I'm audible. So we'll quickly wait for a few minutes for the rest of you to join, and then we'll start with the session today. Let's just wait for a few minutes. So mostly covering many parts of the project, the second project, in this classic art project. Sorry for the background noise. So again, coming to the planning decree, again, most of you have completed the project one, but still, project two you haven't completed. And speaking like only one or two of you have completed the project two itself. So I recommend that please gear things a bit up and complete the project two as well, because again it's high time now, and I guess we have less than 1 month for the narrow degree to get over, and you have two projects in hand. So yes, you have to gear things up and complete it as soon as possible. Uh, and so yeah, project two again. As I said, today's session will. I had thought of getting started with the unsupervised section as well, but since again, as I said, only one or two of you have completed the project two. So, and most of you are planning to complete it this weekend, as I have talked to you guys. So, do complete it by this weekend, as many as of you as you can, so that next week we can start with the unsupervised learning. And as I said, the project two was already project two deadline is already on 5th of May, and it's already 12th of May. So please gear up a bit and complete the project two as soon as possible, so that we'll have enough time to complete project three and complete all the sessions in hand. Again, as I said, that I was going to start with unsupervised learning as well today, but since again most of you have not completed or not started with the unsupervised section, I'll not be including that, and so the today's session will be short, not that long, and we'll be just covering the remaining portions. That is mainly I'll be covering with how what's the best way to save and load a checkpoint, bit a brief introduction about the unsupervised learning, and that's it. And again, I'll be taking questions from you guys if you have any questions regarding the project, any section, anything. I'll be there, so you can ask questions about that as well. So that's how we'll be going on about today. So I think we should start now. So uh, saving. So last week, mostly what we covered was momentum, the need of momentum, learning rate. We talked about dropout and regularization, why it's important. Again, regularization. Again, we talked about how there are multiple ways to prevent overfitting. One of the ways was to have ensemble models. But again, as we talked about, like uh, there are drawbacks of ensemble model, though the accuracy and results would be better by the uh, ensemble technique, but it wasn't a very good idea because of the inefficiency it was providing, like during the testing time, since we know that uh, neural networks are it have a lot of models and we are averaging out the results of each of the model. We know that during the prediction time or the test time, we need real-time results. So in that case, we can't afford multiple calculations through all the models and then combine the results, because again it would decrease the increase the latency and increase the time response time. So that was not a preferable point during prediction and as well as during training. We know that neural networks can sometimes take days to get trained. In that case, we don't want multiple neural networks to get trained at one time, because again, if we are training multiple neural networks, as in the simple method we use, so that will not be best approach or an efficient approach, because we'd have to train multiple neural networks and it would be like very inefficient. So though the results provided by the ensemble methods or ensemble neural networks would be good, but the inefficiency or the drawbacks it has are like it outweighs the results it provides. So there was another approach we talked about, was that introducing dropouts in our neural network. Like again, if we think intuitively, the dropouts work you can think of dropouts as like uh, neural networks. Like there are multiple thinned networks in that one neural network. So in each epoch or in each iteration, we randomly turn off a few neurons, and doing this makes the neural network look like it's a thin network in which some of the neurons are not working or are dead, they are not passing the outputs. So they are like thin networks, and since this neurons are turned off some probability, so at each of the time, some of the neurons will be turned on, and again that particular neuron might be turned on for some other iteration. In that way, it can be like multiple we can have like multiple different configuration of that same neural network. There will be multiple configuration in which some neurons will be turned off in at some time and at some point of time, and while some other might be turned off at some point of time. Again, we talked about how that particular trend network, as we talked about it. So during prediction, we can't have again this multiple thin network to have our prediction, because again it will bring the same problem we had in the ensemble technique, that we'll have to calculate the output of all this multiple during text time, which is not a good way because we need real-time results. So again, we talked about how we can overcome that problem. It was by so we talked about it, since we are turning off the any of the neuron by probability p. So what we will do is that the output provided by that neuron, so the weights of the output that's connected to that particular neuron, will multiply that result with the same probability p. So uh, that helps or that helps us like reduce the problem that we had in multiple networks. So it basically balances off when we multiply the output or the weights connected to that neuron, the output weights connected to that neuron with the same probability p. So it balances the overall result while in the prediction. So basically in the prediction, we don't turn off any of the neurons. Basically, we have all the neurons on, but what we do is that we basically multiply the output waves of that particular neuron with the probability p, so that it balances the thing that we had during training, that it was off or on. So that's how we go on through the prediction time. So that's, and if we talk about PyTorch, do remember that when you're training the model, call this function called modeler train. This function will uh, switch the model in the training mode, and if you want to have prediction or validation or during the testing time, we'll have we just call model eval. So what it will do is that this model, that when you call it model eval, it does these things like if you have a dropout layer, so that each of these output weights are multiplied by that probability which we had passed to the dropout. So these things are taken care internally by PyTorch. So again, if we turn on the training mode, that's model or train PyTorch. So in that case, the model will handle all those inner edges that we talked about in dropouts and other steps, that some of the neurons will get turned off and on. So that will be taken care internally. Just you have to take care of this thing that you call explicitly model or train during the training process, and when you're doing validation or when you're testing your model, uh, call model.eval. And again, when the prediction is validation is over, don't forget to switch back to the training mode, that's model.train. So that's about how we consider about dropouts and basically regularization and prevent overfitting, how to prevent overfitting. That's what we talked about in the last section. We were also uh, so today we'll be focusing on saving and loading a checkpoint. So I thought of including this in the session today, because mostly what happens is that most of the submissions I have seen, what happens is that people, students generally tend to submit the history dictionary, or like, as I said, this is one way of saving the model. Right? If you can see in the presentation right now, there is this save function which I have written. There's toggle save model that is state dictionary. That what basically does is that it takes the entire model, uh, takes the state dictionary, that's weights, basically weights of the uh, basically the hyperparameters, you can think of that. So it takes this state dictionary and it shows in the file that's provided with the path variable. So this is basically one way of saving a model. Uh, Basically, again, if you want to load the model, you need to have the model class, of course, because it has to be the same configuration, the same layers and dropouts and everything. So that has to be there. So if you see here, this is the model class. So you need to create the model, obviously, random weights and whatever. And then you have to load, you have to call this load state dictionary function and pass the loaded dictionary, state dictionary. So to load the state dictionary, you'll call torch.load, again the path of the checkpoint that you have saved here. And this will, and when you call the load state dictionary, it will, what it will do is that it will overwrite all the parameters and hyperparameters and the weights by the saved weights you had saved before, like after the training was complete or whenever you have saved it. So it will overwrite this model. This, when you basically call this the model class, it might have generated the model with, say, random inputs. But when you call this model.load state dictionary, it will override all the weights and parameters by the weights in that checkpoint file. So this is one way to save and load a model in PyTorch. Again, you can see this model.eval function here. Again, generally what you do is that you train the model and then you save it. Or sometimes what you do is that you partially train the model and then you save the model in checkpoint. But again, in both the cases, you need to save the model properly. This is one way to save the model. Again, this is model that eval I was talking about a few minutes back, about how model eval needs to be there so that it takes care of these dropout things that uh, during model.eval is basically the validation or testing phase. So when you call that model.eval on any on the model, it will take care of this, that the model is in testing mode and not in training mode, and by this it takes care of multiple things. Among them, one is that it takes care of this dropout layer. So what happens, as we know that in dropouts layer, uh, in the testing mode, basically we don't turn off the neurons individually. So what we do is that we multiply the outputs of each of the neuron with the same probability, that's p, by which you turned off that particular neuron while training. So that's taken care when you turn the model into in the evaluation mode or prediction mode. So these things will be taken care of when we take in the model to evaluation mode. So that's how we handle saving and loading the models. So this is what I was talking. And when you turn on the training mode, that will have to just call model at train, and it will take care of this turning, switching off neurons and stuff. So this is one way to save a model. That's just save the state dictionary in a checkpoint file as provided at the path, and then load it simply by calling the load state dictionary. And again, this is not a very efficient way. It does helps us, but it's not the most efficient way of saving and loading the model. We'll see some other techniques as well. Moving on to the next slide. Another way is again to save the entire model as it is. So you just need to call toss save, pass the model and pass the path, file path, and it will save the entire model as it is. And it's like very simple and efficient to use. Like when you want to load the model, just call toss.load, pass the path, and you get the entire model as it is. So the benefits of this procedure is that you don't need to remember the model class. So once you save the model, you just need to call toss.load, and irrespective of where you are. So if you see in the previous example, you needed to have this the model class. So you needed to load, you needed to have the function the class defined, how the layers were defined and everything. But in this particular example, or in this particular scenario, uh, you don't need to remember. So any third person, anyone, just you can just give the checkpoint file, and they can directly load the model from the uh, toss.load, and they can use it directly without knowing how the model is defined. So again, they can see how the model by various Python function, like model of summary, etc. But again, it's very simple, and it's like a wrapper or something that you can directly load the model without knowing the internal details or at any time, at any point of time. But the what the problem is with this kind of saving and loading a model is that in this case, suppose you want to retrain your model. In that case, again, you'll not know what exactly your model is, because you're just loading it from the toss.load. So if you want to start or retrain or continue training, so suppose you had partially trained your model and you want to retrain it again, that might become a bit difficult. So in this case, that's one problem. That's not the major problem in there. The most difficult, or the most like difficult problem in this kind of scenario is that the size of the model is very large, very huge, because you're saving everything in a checkpoint file. So that's not a very good way or desired process. So generally, as you know, the if you are saving the entire model as it is in your checkpoint file, it includes everything, all the torch internal local variables and everything. So it will save everything, and the size will be like very huge. Definitely not a recommended way. And if you talk about your scenario, in our scenario of the project 2, we have like most of the we use transfer learning, which majority part, there's a feature extracted part, which is the most deeper network, deeper part of the network. We have just turned off everything, and it's available in the torch library itself. It's just, if you want to, if you're saving the entire model, in that case it's like redundant. It's not at all useful, because we have everything, and why do you want to save it again? So obviously don't want to do that. And if you talk about your GPU in the workspace provided, you have a limit of the size. So again, it's not at all recommended, or it's not feasible, or you won't be able to basically do it. Because if you use GPU and there's a size restriction of, I say, 1 GB or 3 GB, so you'll not be able to save the model in this format, that you save the entire model. So again, this is not the recommended approach to save the model. Again, as I said, the previous two approaches were not at all efficient. They consume a lot of memory, and obviously the first one doesn't consume a lot of memory, but the problem with that is that you can't start retraining your model or something. So that's the problem in the first approach. Uh, Again, it consumes a lot of memory. It's definitely not recommendable in case of at least transfer learning models. So we'll talk about the efficient way of saving the model. So another approach is to save the parameters as a say dictionary. So as you can see in the example here, so we are saving all the hyperparameters and the state dictionary. So we are saving the epoch we have completed. We are a number of epochs we have trained for. We are saving the state dictionary of the model. We are saving the optimizers dictionary so that we can obviously restart the training process if we want. We are saving the logs and everything that's important. So this is the so we basically save all the hyperparameters. So in our case especially, we don't even need to save the entire state dictionary. You can just save the model that classifies a state dictionary because that's what we are working on. And the feature extractor part is, we are not even touching the feature extractor part. So we can assume that the feature extractor part is not being used, and you don't need to save that. Again, the lot is state dictionary. This is not like the huger part. It's not that big in size. So you can just save the model at state dictionary, but you can also just save the model at classified at state dictionary. And when you are loading the model, you can just load the whatever uh, base model you are using and just override the classifier's state dictionary, not the entire state dictionary. So again, uh, loading the model is again simple enough. Just you need to load the model class. You need to load the checkpoint. You need to load the state dictionary. You need to load the optimizer state dictionary, and you need to see where what are the hyperparameters were, and you can restart the training process or continue with the validation prediction process. So if we talk about the uh, our project. Again, if we especially talk about the second part, there's the scripts, the prediction script. In the prediction script, you are supposed to write a script in which you need to load the checkpoint and you need to build the entire model. And if you know about if you have seen the project or gone through the rubrics, if you might know that in the training process, you are supposed to allow the user of the training script to choose between multiple architectures. So by multiple architectures, I mean that between BGG16 or say DenseNet or say AlexNet or say ResNet. So you need to provide options to the user, at least two options, and the user needs to choose from those two those provided architectures. So you need to build the load checkpoint function that you need to build in the prediction or the parameters you are saving in the checkpoint should be like generic enough so that you can load any model, because you know that there are multiple models that can be could have been chosen during the training phase. So in the prediction mode, what you can do is that you can save the architecture name of the model that was used during the training or that was chosen by the user, and then you can use this get attribute function, that is GETATTR. It's the get attribute function of Python, and you can just pass that a models library from Torch, PyTorch library, and you can extract that particular architecture by just getting this passing using this get attribute function. You can pass this models library, and then you can pass the a particular whatever architecture name it was, which is basically saved in the PyTorch also. So this in this way, if you call get attribute and this function the models and the architecture name, you can generically load any model. If you want to know, if you want to get about the detail or the code part, do let me know. I will post it in the Slack section. in the Slack what's exactly what I'm talking about. So that's about saving and loading a model, and it's important part. Don't save the entire model. Save all the hyperparameters, especially the architecture name, the learning rate, and the state dictionary. Obviously, as the most important one, and all of these things. Save all the important hyperparameters in your model in your checkpoint as a dictionary, so that it's you can continue training the model or the testing or validation part. So save all the necessary hyperparameters, save it in an efficient way, not just dumping the entire model in the checkpoint. So this is what about this is what was about saving and loading model. Now, uh, validation testing data. One thing that I have noticed again in most of the submissions, that the validation and testing data, you try sometimes you like use the test data during the validation process, or you use the test data for generally people students. What they do is that use the same test data for validation and the post validation as a testing phase. Do you need to understand that these two are different validation and test data. These two are totally different data sets, uh, and it's purposely uh, separated out. So we are purposely uh, like that training data, it should be as huge as possible, but we are purposely taking out two subsets: validation and test data. If test data was only enough, we wouldn't just purposely decrease the size of our training data. But we are doing that because validation and testing both are important phases of any uh, 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 training paths. So why it is important is that, so let's say, as I said, most of the students tend to use the same test data for validation, which is definitely not the way to go on. So if you use, so what is the validation used for? So validation is generally used for, that validation is used for tuning the hyperparameters, mainly say tuning the learning rate or stuff like that. Yeah. So that's what validation data is used for. So during the training process, say let's say one epoch is over, and you can see that your model is overfitting or something like that. So in that case, you can say tune the parameters, say the learning rate or some other parameters here, which can prevent overfitting. So that's where validation data is used. So if you use the same value, so what is happening is that you are using that validation data and you are tuning your parameters so that your training or your model gets learns properly. So some way the validation data already knows about your data set, because it helped the model learn more about the data. If you use that same validation data for testing, or you already use the test data for validation, so what's happening is that again the test data is what should be that. So this again, if you talk about the image, the any online competition or something, in that case there are many submissions to any problem, and there is a test data on which each of these predictions are tested, and there is a common ground that all of these models don't know nothing about the test data. So the test data is new to the basically all the entire models. So if it is only and only if the data is new, in that case only the will get the actual accuracy of the model. So if the model has already seen that particular data, you will not get the correct the true accuracy. So to get the true or correct accuracy, it's important that the model hasn't seen that particular test data. So that's why we see that we need different sets, different subsets of data set. So we need to have a different validation set so that we can tune the model so that we don't have overfitting and stuff like that. And we need a different test data so that we can have a true accuracy of the model. A data set the model has never seen, or it has never been fitted on that data set. So that's why we need to have different validation and test data set. Do remember to use different validation and test data set for your training and testing purposes. I especially included this part because most of the students do this part, that they mix up this validation and test data, which should not be done. So moving on. Now, the image classifier project. Again, one important thing that I have noticed across the submissions is that generally what you do is that you use the same pre-processing libraries that you the transform basically when you call the image loader or the data loader and the image loader. So you remember the image folder thing? You had a transforms argument in which you could pass this resize, center, crop, and stuff. So there, you could pass the resize and center crop, and PyTorch was internally pre-processing the image. But especially for the process image function that you had to write, you need to use the native library for pre-processing. You can't use that same transforms. Again, it doesn't make any difference to use that transforms or you use this native library. But for learning purposes, it's highly recommended that you use the native library. You need to resize, you need to spill library and PIL library and native whatever Python native packages are there, and then you need to manually resize it, take care of you know uh, take care of proper resizing. You need to uh, uh, resize it before cropping. Obviously, you need to uh, uh, obviously you need to resize and then crop, and anything like standardization, that all needs to be done using native library and not the directly used transforms that you had defined, or you use PyTorch transforms. You don't need to use PyTorch transform. You need to use Python native library for pre-processing, resizing, cropping, and standardization, basically normalization. So remember this, because again this is one of the common mistakes in most of the submissions I find. Moving on, predict function. Again, this is the important thing. There's the class to index mapping. So the classes and indexes, these both things are basically integer values. So both are 1, 2, 3. So when you use top k values, you basically get indexes. You need to get the reverse class to index mapping, that is index to class mapping, and from the indexes that you get from top key function, you need to get the actual classes. So that's important thing, and then you can apply the category to name, cat to name mapping, because the cat to name mapping is only classes. So you have the classes, and only then you can apply the cat to name mapping to get the actual name of those flower images. So before getting, and how do you get the classes? You need to apply the index to class mapping, and then only you can get the actual flower name. So this is one important thing, that students don't apply the index to class mapping, and they get the indexes. They think this is the class, and then they directly apply the class cat to name mapping to get the flower name, which is actually wrong. And the confusion comes here due to the fact that these both classes and indexes are basically integers. They are both 1 to something and 1 to something. That's why the confusion comes in. So do remember to apply the index to class mapping as well. Uh, that's about predict function. Again, the predict function internally calls the process image so that the processing part is done. Again, you need to get the top 5, so you need to use the top key function. This is about the predict function. Now, the training scripts. Again, do read the guidelines very properly. Their training script should be self-sufficient. It should take all the command line arguments. The support for command line arguments is a must. They should provide support for all these command line arguments. We should provide the command to run in a comment or something, and then whatever support for command line, like the multiple architecture support. After the multiple architecture support is present, you need to take care of the input size of different architectures, because if you see the classifier part and the feature part, as you know, there are multiple architectures. So let's say there are DenseNet 121 and there's VGG 16. So in VGG 16, the classifier part, whatever it is, the feature extractor part returns the output size of the last layer of the feature extractor part in VGG 16 is 25,088. While in DenseNet 121, the last output of that feature part, the feature network, is 1024. So when you are overwriting the classifier of these two dictionaries or these two sorry models, you need to specifically take care of this output size of the last layer of the feature part, so that when you rewrite your classifier part, you know that what is the input size of the first layer of the classifier part should be. It should be equal to the output size of the last layer of the feature extractor network. Again, I'll repeat this sentence, that as we know, any of the transfer learning models we know, or the PyTorch libraries or models we know, they have two parts. There's a feature extractor part, and there's this classifier part, which is fully connected networks. The feature, uh, due to the essence of transfer learning, we set the gradients of the feature extractor part to 0, and we don't train the feature extractor part because it's already trained. We just train our classifier path, and we overwrite or rewrite the entire classifier part with our own uh, layers, and basically we custom write our classifier part, just the classifier part, because that's what we need to train and learn. But to build this classifier part, we must know what should be the input size of the first layer of that classifier, because again we are connected to the feature extractor part. So just after the feature extractor part, the last layer of the feature extractor part output is done, we need to take that input and feed it into the classifier network. So to build the classifier network, we need to know the output size of the last layer of the feature extractor part. So we need to take care that uh, whichever network it is, the last the classifier we built needs to have the correct input size. So that input size, so let's say for VGG class, we need to use model.classifier 0 in features through this function. That's basically uh, whatever classifier we had previously, the zeroth, because it's an array or a dictionary, we take the zeroth layer and take the in features, in underscore features, and then we know what is the input size of, what was the input size of the last the default classifier, because the default classifier would have correctly handled this feature and classifier gap. So you can use that and get the input size. Again, for denseness type, again for each of these models, the classifier part is different. So VGG, we have a list of different layers, so we can use model that classifies 0 features. But if we talk about denseness, it's just one particular layer, one fully connected layer as a classifier. So in that case, you need to just use model.classifier.in features, directly model.classifier.in features, not model.classifier of 0.in features. So that's one important thing to remember, that when you are training, when you have providing multiple architecture support, you need to handle this input side of the classifier differently for different models. So that's important thing. Again, you need to check for hyperparameters like learning rate, epochs, hidden units. Again, hidden units need to be a multiple, command line argument. So you need to take the user's input and then accordingly build out the classifier using this hidden units provided by the user. Again, one important command line argument is device. So the user's choice of device. In that case also, even if the user chooses to use GPU for training, you need to specifically test that whether GPU is available or not. And only if GPU is available and the user chooses for GPU, only then you should choose to train on GPU, else you'll have to switch to CPU. And vice versa, that even if even if GPU is available, and but still the user chooses to use CPU, you need to specifically use CPU even though GPU is available. So you need to take care of both these conditions, that the user chooses GPU and GPU is available. So the GPU availability you can check using torch.quda.is underscore available. So this function will provide you if GPU is available or not. So you need to take care of both these things, that GPU availability and user's choice of device, and then only choose to train on GPU. So this is one thing. Moving on to the prediction script, again read the guidelines very carefully. You'll have to load the checkpoint from the checkpoint, load the model from the checkpoint generically, because there might be more than one model, because there was a choice to choose models between in the training script. You need to save the architecture name in the training script and use that architecture name to load the same model in the prediction script. So that's one important thing. Again, the top key and JSON file path needs to be command line arguments. Again, the same thing goes for device here as well. You need to specifically choose uh, GPU or CPU based on both GPU availability and user's choice of GPU for prediction part as well. So this is about the prediction script and training scripts. Uh, Unsupervised learning, as I said, we'll cover it in the next session, because most of you have not completed the project 2 as well. So these are the important things which I thought was important for the image classified project. Now I'll take questions if you have any. Let me know if you have any questions and I will answer it. If you don't have any questions, you can also ask me directly or in the group we have, so that we can discuss it. We can discuss this, with your other classmates. We can discuss with you, and all of you can benefit from it. So do let me know that as well. I'll just wait. And as I said, we'll cover the unsupervised learning. I had already prepared, but we'll cover it in the next session. If you have any questions, please do post and we'll cover it. If you don't, again, you can post it in the session or in the indirect message with me. You can ask me in the 1:1 session as well. Again, most of you have not completed project 2 is still. Please do hurry up. Uh, and will start unsupervised learning, and I want that all of you should have completed project 2 before that and have started working on the unsupervised section, because I guess less than 1 month is left for uh, the nano degree to get over. Please, if you have any questions as of now, please do post. Okay, if you don't have any questions as of now, we'll cover it. If you have it, you can ask me in this channel or something. Please complete it by the weekend. As most of you have informed me that you're going to complete it mostly by the weekend. I hope you'll do. Again, waiting for you all to complete the project. If you have any questions, please do post. And again, if you go ahead and book a slot for 1:1 session, we can catch up and stuff. So till then, I guess this will be it for this session. And again, we'll from 1:30, we'll be having asking anything session. So post your questions in there as well. Again, if timing doesn't suit you for the session, if you want anything to be included in the session, do let me know so that I can include it. So you are going to start up with the new section on supervised learning. If you specifically want me to include something in the sessions, do let me know there as well. So if that's it, we'll end this session today. And bye. Thanks for watching.